In this video, we explain how the molar Gibbs energy changes with temperature. There's two things that you need to know about this material before we get started with the video. The first one is that the molar Gibbs energy is the thermodynamic property that controls the stability of a phase of a substance. For example, when we say that the liquid phase of water is the stable phase at 25 Celsius at 1 bar, then that is because the molar Gibbs energy of the liquid phase is lower than the molar Gibbs energy of the other two phases, the gas and the solid. Okay, so again, the molar Gibbs energy is the thermodynamic property that controls the stability of a phase of a substance. Now, in a second video, we have studied how the molar Gibbs energy depends on the conditions. And then what we learned is the molar Gibbs energy only depends on two variables. One of them is the pressure, and the dependence is through the molar volume. And the second one is temperature, and the dependence is through the minus molar entropy. Okay, so in a prior video we studied this dependence very well. And then what we're going to do right here is study how the molar Gibbs energy depends on the other variable, the temperature. Okay, so to do that, what we actually do is consider that the pressure is constant, and then if the pressure is constant, this differential of P is 0, and all of these terms vanishes. This term vanish. Okay, so we can erase that and then do this. Okay, so we can rewrite this expression as simply this minus molar entropy differential of T. Okay, all right. There's another way to write this expression that is used frequently, and that is to use what we call partial derivatives. Okay, so the variation of the molar Gibbs energy on temperature at constant pressure is going to be equal to the minus molar entropy. Okay, so this tells you how the molar Gibbs energy changes with temperature. And what that tells you is that that depends on the molar entropy. The question is, well, what is the molar entropy of the phase of a substance? Well, we know that entropy is related to the disorder of the substance, so something that we have learned earlier is that the molar entropy of the gas phase of a substance is greater. This gas is more disordered than the liquid, okay, and than the solid. Okay. Now, what are typical values for these molar entropies? Well, we know that the third law of thermodynamics tells us what is the lowest value that these entropies can have, and that value is 0 when you have a perfectly crystalline substance at 0 Kelvin. At any temperature above 0 Kelvin, which is where we're going to be working, then the molar entropies are going to be positive. Okay, so all of these numbers will be positive, even if they are ranked this way. So, for example, for water, gas at 25 Celsius and 1 bar, the molar entropy of the gas is equal to 188, more or less, joules per mole Kelvin. But for the liquid phase, this is going to be 69.9 joules per mole Kelvin. Okay, so again, you can see here that a gas is clearly more disordered than the liquid, and then than the solid. All right, so now that we understand that these numbers are all positive, then we can try to figure out what will be the change of the Gibbs energy with temperature. Right, so if we make the differential of T, the change in temperature, positive, that means that we're increasing the temperature, then because this number is positive, but it has a negative sign in front of it, then that means that all of this is going to be negative. Okay, so if this is positive and that is negative, then what that means is that the differential of U will be negative. Okay, so the change in the molar Gibbs energy when you increase the temperature actually is negative. That means that the molar Gibbs energy decreases with increase in temperature. Okay, you can verify that with this expression. You make this positive, then this is going to be negative, which means that the change in the molar Gibbs energy will be negative. And again, that means that when you increase the temperature, the molar Gibbs energy goes down. Okay, great. So what else can we learn about these things? Well, the other thing that we can learn about this thing is that notice that this is the first derivative of a function with respect to the variable. Okay, and that is actually the slope of a curve where you will represent the function with respect to the variable. Okay, so much as we did before with the molar Gibbs energy and pressure, what we can actually do is draw a graph of the function, the molar Gibbs energy with respect to temperature, and then we will know what the slope of those curves will be at any point. Okay, and that will be the minus molar entropy. All right, so let's see if we can actually draw that. Okay, so this is how this graph looks like. You have here the molar Gibbs energy versus temperature. and this is at constant pressure. Right, so you're going to have here lines for each one of the phases, okay? And the slopes are going to correspond to the minus molar entropy of each one of the phases. We know that a gas is more disordered than a liquid and a solid. Okay, that means that the slope of the gas line will be greater than the slope of the liquid and the solid lines. These are all going to be negative slopes, so they're going to be pointing down. Right, so for a gas, the way that this line would look like is something like this. Again, the slope of this line is equal to the minus molar entropy of the gas. Now, a liquid is also going to have a negative slope, but the value of the slope, the absolute value, is going to be smaller than that of the gas, because the liquid is intrinsically more ordered than a gas. All right, so we're going to draw here a line with negative slope. That will be the liquid. But notice that the slope is actually a little bit less than that for the gas. Okay, so that slope is minus the molar entropy of the liquid. And we also have the solid. Okay, so the solid is also going to have a negative slope, but it's going to be the least steep of the three. Okay, so we can draw the solid like this. Okay, so still is pointing down. It's barely pointing down, but it should be pointing down. Okay, that is the solid, and the slope is equal to the minus molar entropy of the solid. Right, so what can we learn from this graph? Okay, notice that what we have here is the Molar-Gibbs energy for the three phases as a function of temperature. Because the Molar-Gibbs energy determines what is the stable phase is, we can just analyze the values of the Molar-Gibbs energies of the three phases and then determine what is the stable phase at any particular set of temperatures. For example, if you go at very high temperatures, we see that the Molar-Gibbs energy of the gas is here, that of the liquid is here, and that of the solid is there. Okay? Clearly, the Molar-Gibbs energy of the gas is the lowest of the three. And what that means is that the gas is going to be the stable phase at high temperatures. This makes perfect sense because we know that when we have any substance, if we elevate the temperature high enough, then that substance will turn into a gas. Okay, so that's great. It means that from this point on, okay, the gas is the stable phase at any temperature that you want. Okay, at this particular point, something interesting happens, and that is that the Molar-Gibbs energy of the liquid is identical to the Molar-Gibbs energy of the gas. At that point, we have an equilibrium, right? No phase is more stable than the other. You have that some of the liquid will be turning into the gas, but some of the gas will be turning into the liquid. That's what we call the vaporization condensation equilibrium, right? And that would be the vaporization temperature. Okay, so if this would be 1 bar of pressure, constant pressure, and this substance happens to be water, then this temperature will be 100 Celsius. Okay, if you cool below this point, then notice that the stable phase is no longer the gas. The phase with lowest Molar-Gibbs energy in this point is going to be the liquid. And that happens all the way until this point where you actually cross with the solid line. Okay, so the liquid is the stable phase in this range. And then at this particular point, what we have is that the Molar-Gibbs energy of the gas and of the liquid and the solid are identical, and that is the fusion, melting, freezing point. Okay, at that particular pressure. So for water at 1 bar, that will be 0 Celsius. Well, if you cool below this temperature, then notice that the phase that has lowest Molar-Gibbs energy is the solid. Again, so this makes perfect sense, right? You cool the temperature. If you cool the temperature down sufficiently, every single substance will turn into a solid. When you elevate the temperature, you may go through the liquid, but eventually you will always end up in the gas. Okay? So notice how this very simple expression, where you just examine the dependence of the Molar-Gibbs energy on temperature, it really bears out what we actually know about the substances, right? And the phase stability with temperature. All right, there's another crossing of the lines, which is right here, and that is this one. Okay, and the question is, well, that is the crossing of the solid and the gas line. Would that be sublimation? And the answer is, in principle, yes, but in this graph is inconsequential, because this crossing is between two lines that are not that do not represent the stable phase at that condition, right? Notice that under this condition of temperature is the liquid line, the one that is the phase that is stable, right? So that crossing happens, but it's entirely inconsequential, and you cannot write here that this is the sublimation point, because this substance does not undergo sublimation. Okay, what we can actually do then is try to see how would this graph look like for a substance that undergoes sublimation, like CO2 at 1 bar. Okay, well, for CO2, 1 bar, the way that this would look like is as follows. You have that the liquid phase is never stable, right? You have dry ice, and then you elevate the temperature, and that turns into the gas directly. There's no liquid phase stable at 1 bar of pressure. How would that graph look like? Well, you will have that this is the line of the solid, this is the line of the gas, okay? And then the liquid line is never below these two, right? So a way to draw this will be like this. The slope is intermediate between them two, okay? But at no point the liquid phase is stable. Under this particular point, that is what we call the sublimation temperature, okay? And for CO2, that's how this graph looks like. Okay, so this is kind of an introduction to how the Moore-Gibbs energy depends on temperature. In the next set of videos, what we're actually going to do is try to add a little bit of complexity to this by showing a new set of lines that will happen at a slightly different pressure, okay, to see how both temperature and pressure affect this graph and what can we learn from phase stability from those representations.